So now let's talk about the area underneath the curve. So as we've covered before, the area under velocity time graph will be equal to the displacement. And we can use the graph to calculate the displacement at various increments. Please do that now, pause the video, and return when you've done that. Don't forget that the area under the horizontal axis will be negative. Okay, so hopefully you filled out your graph now, but we'll do one example here. At 40 seconds, we have the area under the graph as the expression given here. The area above is 30 seconds times 3 meters per second equals 90 meters, plus 10 seconds times negative 3 meters per second gives us a total of 60 meters. And if we fill out the rest of the displacement time chart, it looks like this. At 0 time, 0 displacement. Moves up at 30 seconds, we have our maximum displacement, and then it drops back down to 0 by 60 seconds, as we would expect. So let's go ahead and plot the points in this table with time on the horizontal axis. So we're going to get a displacement time graph. Go ahead and pause the movie, please, and do that now. Okay, so this is what we should look like. We've got a pretty simple triangle where the displacement increases as we move away from origin, and then when we turn around and come back, the displacement decreases back down to 0. And of course, Leah's at 0 displacement at the end of 1 minute, as we'd expect at her starting point. Okay, but we can find the average velocity over any time interval by taking the slope from the displacement time graph. So please go ahead and determine the average velocity over the 1 minute time interval. And hopefully you got 0 meters per second. Since the displacement was 0, that divided by the 60 seconds is 0 meters per second. All right, so let's look at this displacement time graph of a radio-controlled car. We've got positive moving forward, negative moving back, of course. Go ahead and on a separate sheet of graph paper, describe each of the segment in words and sketch the corresponding distance time graph. Notice that it's distance time, not displacement time, so it won't look the same. And when you're finished, also sketch the velocity time graph. Go ahead and pause the movie, please, and work on that. Okay, describing the segments in words. You should practice doing this. It's a good exercise, and it will be on various quizzes. So we have the first segment. Between 0 and 2 seconds, the car is traveling at 4 meters per second forward, right? Its displacement is increasing, and it's at a constant rate, and our slope gives us 4 meters per second. Now, what about between 2 and 4 seconds? Well, we can see that our slope is 0, so our speed is 0 and our velocity is 0. The car is at rest. Now, between 4 seconds and 9 seconds, we have a negative slope, meaning that the car is moving backwards. We can extract that slope pretty simply and get the car moving backwards at 2 meters per second. Finally, the segment between 9 and 10 seconds. Again, the slope is 0. The car is at rest. Now, in terms of the distance time graph, this is a very important exercise to work on. So please go ahead and do that. Pause the movie, go through and calculate the distance time graph, not the displacement time graph. All right, so the first segment is given here. We've got, again, always define our axes, distance in meters versus time in seconds. And as the car is moving forward, this segment looks exactly like our velocity time graph, or our displacement time graph. And similarly, the car being at rest gives us zero slope, zero change in distance across that 2-second segment. Now here's what's interesting. Where previously, you'll remember that since the car was moving backwards, we had a negative slope moving downward to the 9-second point. In this case, because we're only plotting distance traveled, that segment is in fact positive. So the car is moving, and all we're measuring is movement, not distance when we're doing displacement. The car is moving, just moving slower. It's got a smaller slope, 2 meters per second. And the last segment, of course, the car isn't moving, it's at rest. And again, negative slope for the last second. So this is a very important distinction, and you need to be able to draw these distance time graphs and move back and forth between distance time and displacement time graphs. Okay, sketching the corresponding velocity time graph. Please go ahead and pause the movie and do that now. Okay, now welcome back. Here is my sketch of the velocity time graph. You can see, remember, we were at 4 meters per second for the first 2 seconds. Constant speed. There's a discontinuity. Then we're at 0 meters per second for 2 seconds. At -2, remember this is velocity, so there's direction, -2 meters per second from 4 seconds to 9 seconds. Another discontinuity, and then 0 meters per second for the last 1 second segment.